Today's agenda will start with an introduction to CPU load, then we'll look at different methods to measure CPU load, 2 that require code instrumentation, and 2 that don't require any code instrumentation. Then I'll demonstrate the 2 non-instrumented profiling methods using a couple Infineon TC399 target boards. Before we get started, I want to mention a webinar by my colleague Felix from August of last year on CPU load analysis called Understanding Linux Process Load Compared to Embedded RTOS Utilization. He provides a thorough look into the definition of CPU load and CPU utilization and how in embedded software development, which is the domain I'll be concentrating on today, they basically mean the same thing and can be used interchangeably. Having said that, in today's intro I'll take a very simplified look at CPU load analysis. For example, let's say we have a CPU, we'll make it a single core CPU. The CPU is expected to be under load during measurement, therefore any low power or sleep modes are typically disabled. For the purpose of CPU load analysis, we look at the system as having 2 states, idle or executing. It is up to you to determine what you consider idle code and executing, or active code is another common term. That leaves 3 times: measured time, idle time, and executing time. And we have a nice simple equation. The measured time equals the idle time plus the executing time. So now that we have the time spent executing and the total measured time, then we can define CPU load as the ratio of executing time over measured time, represented by L. We can see the ratio will be between 0 and 1 and therefore is typically represented as a percentage, as we can see in this example. Another way to calculate CPU load would be to measure the idle time, and then CPU load becomes 1 minus idle time over the measured time. And our example yields the same result. CPU load for a multi-core CPU with n cores can be calculated by simply taking the average of all individual core loads, and of course the idle time can be used to calculate a multi-core CPU load as well. And we'll soon find out measuring idle time is the quickest way to get an accurate measure of what the system is doing. Since we want to know the CPU load over a period of time, we need to decide how often we want to average the load data. WinIdea provides an average over the total measured time, but the min and max values will deviate depending on the period set for the averaging window. Too short a period and we only see 0% for idle time and 100% for executing time. We need to take a step back and get a more useful picture of what's going on. But too long a period will average out some local overloads, and they won't be visible in the profiler timeline. I'll demonstrate this in the profiler later. Now let's look at 4 different ways of measuring CPU load. First we'll go over the 4 methods and then look at some pros and cons of each method. We have instrumentation by the user. This is where you add some code to measure either the time spent in the idle code or time spent in the executing code. Next we have load measured by OS. This is where the OS has some built-in load measurement code. Next we have the no-instrumentation trace-based profiling. This is what you can do in WinIdea if you have access to a hardware trace port on your target, like a Nexus or ETM or Aurora. Later in the demo I'll show our analyzer and the profiler statistics and the new CPU load inspector. Finally, I'll show our no-instrumentation sample-based profiling, which only requires a debug port. No trace port is required. The easiest way to add CPU load measurement to your code is to instrument the OS idle task with measurement code that calculates the ratio of idle time versus overall runtime. The main benefit to this method is there's no extra tools required, but you do have to add code to your project, which adds some overhead. And this is the bare minimum for CPU load. If you do have an overloaded system, you aren't going to get any info about what code is executing, causing that overload. For that, you'd need to add some more code or tools like an iSystem debugger. The next method we'll discuss is CPU load measurement by the OS. Most RTOS or AutoSAR OSs have some measurement code built into the system to calculate CPU load based on the idle time. One added pro is the instrumentation can usually be enabled through some OS configuration tool, which makes it very easy to use. Cons are the need for an OS idle task to be instrumented by the OS. The user background task would need to be manually instrumented using the previous method. The averaging window is fixed for each build, and it may cost extra for this feature. Here's a screenshot from WinIdea which shows the OS variable current load with a value of 25, which is the CPU load in %. In the profiler timeline shown at the bottom, we have the hardware trace recording both idle time and executing time and calculating the CPU load, which is 24.4%. While the two previous methods used extra code to measure and CPU time to calculate CPU load, which is overhead, the remaining methods require no code instrumentation and instead use a combination of the microcontroller and the debug tool to measure executing and idle time. For the hardware trace, the chip must support some kind of trace interface. Trace is where the microcontroller has additional logic to non-intrusively record or trace events during runtime. The trace messages can be stored in memory or sent to a trace port where a debug tool like our IC5700 can record the messages. To measure CPU load in an OS-based system, the trace can record all accesses to the running task and ISR2 variable with timestamps. There are many benefits to this method. There's no overhead from code instrumentation. The trace can record all task and ISR execution as well as idle time, which allows greater analysis of timing issues. You can see CPU load over time and see the tasks and ISRs that are running at any moment in time. The only downside is you often need extra hardware like a special device that has the trace pins or trace memory. We sell several emulation adapters that allow you to use a larger pin device on your target to get the extra trace pins or memory. Here's a picture of a couple emulation adapters and the link to view all our emulation adapters on our website. Finally, we have a new method of sampling the data needed to calculate CPU load during runtime. The debugger can sample the running task and ISR2 variables, same as the hardware trace method, but over the debug port while the CPU is running. The positives are you don't need any special emulation device or adapter like the trace method uses, and you still don't need any code instrumentation. The negatives are this method only yields statistical information and the sample rate is too low to capture all idle or executing code. But surprisingly, this method works extremely well to give a nice CPU load running average over time, and it's so quick and easy to configure and get results. Now on to the demonstration. First, I'll show you how quick and easy it is to configure the sample-based CPU load measurement by creating a new workspace for TC399XP production device, which has no trace, just a DAP port. Then we'll take a look at the trace-based CPU load measurement on a TC399XE using the Aurora Gigabit trace port. To show you how easy it is to do a CPU analysis based on sampling, I'd like to create a new WinIdea workspace now and set the configuration for sample-based CPU load analysis. So let's get started under File, Workspace, New Workspace. Here I'll provide a name for the workspace, DAP AP sampling, and this location is fine. iSystem Development Tools is the correct debugger. The device, so we're using a TC399XP production device. This device only has a 10-pin DAP port, no hardware trace interface. Now we have to select our ELF file. And we're going to be using that as the same file to program the system. So now we can click OK. So now we can pick our IC5700 that we have connected here. Next we have some standard evaluation boards listed with preset detailed CPU settings and links to board information online. Since we're using a custom board, we'll select My Board is not listed to continue with the setup. The next setting will be more CPU specific, which is RX in this case. So let's go to Hardware CPU Options. This is where any initialization can be set up. We're not using any for this project. Let's look at the Analyzer section. Since we are using a production device without any trace, we see here the operating mode is grayed out. This is to show we'll be using the sample-based method to measure CPU load. Under SoC, we can select the DAP speed. Since we're using an active probe, we can set up to 160 MHz DAP clock. 160 MHz can be unstable if the target PCB is not designed properly. We want to achieve a high sampling rate, so let's set 100 MHz, which is usually a safe setting. That's really all we need in this dialog for the sample-based CPU load measurement. The next step is to configure our debug session. So let's go to Debug, Configure Session. We see the default application space that is created. Let's check what we have set up for app. The symbol file used for debugging is our testsuite.elf. The next configuration is the OS. WinIDEA supports a number of operating systems. In this example, we're using the Vector Microsar operating system, which is an AutoSAR OS. We typically use an ORT file for this AutoSAR awareness. In this case, because we're using sampling-based approach, the ORT file is not sufficient. We need to extend the ORT file with some iSystem-specific configurations. So we choose an iSystem XML file in this case, which is an iSystem proprietary format which imports an ORT file. We select our XML file, which is specific to this Microsar project. It defines which OS variables need to be sampled to measure all tasks and ISRs running over time and covers all 6 cores. The next configuration is on the SoC level. We've already selected our device. Now we need to select our probe, and in this case we have a DAP active probe. Next is the SMP, or symmetric multiprocessing configuration. So we want to create a new configuration and give it a name. And we're going to include the cores we want in this SMP configuration. Now we need to map the application space to the memory space. And so we're going to create a new memory space here. And we're going to map it to the SMP configuration. And we're going to map that to the application. And we have our configuration down there. Oops. Next, we want to make sure we have all the program files listed that need to be programmed to the internal flash. That's under Program Files. If you have additional boot files that need to be programmed to the target, they can be listed here. Now we're ready to do a download. Now we're sitting here at the reset vector. Let's go ahead and run the CPU. And we'll go ahead and stop it to make sure things are running. Okay, yeah, it looks like everything's good. We'll go ahead and run again. Now we want to take a look at the analyzer configuration for the CPU load analysis. That's under View, Analyzer. So we want to configure it under the hammer icon. And in here we're going to be configuring the profiler. And we can see that the OS objects have been brought in from the XML file. And we're actually only interested in the ISR and task load info. So we're going to go ahead and uncheck the options we're not interested in, which is these running ISR and running task data. So these are variables that the operating system uses, and the debugger can sample this data while the system's running, and this is how we gather the time spent executing or time spent idle. So each value here has an expression that's specified inside the XML file, and that's how the debugger knows to sample these variables. Okay, now we can start a trace. And I can let this run for quite a long time. I'll go ahead and let it run for about a minute and stop it, and we'll fast forward up to that point. Okay, so I've gone ahead and stopped it. We collected 59.821 seconds. So let's take a look at what we've got. We need to expand the data section. We can get rid of this coverage section here. Now we can expand out the task load areas. Let's say, for instance, we're only interested in the task data. So let's go ahead and wildcard that. Now when we expand all this stuff, we should just see the task information. Okay, so now let's go ahead and zoom out. Okay, and we can see all the different sampled data that we have here over the whole 59 seconds. So at any point in time, we can look. So it looks like now we have our background task and the different idle tasks. So we can also take a look at the statistics view. And we have an average value, min value, and a max value. Let's see, we'll put this over here. We can also filter on this side. And so here we're shown statistics for all the different tasks that we looked at. We can also look at the ISR data if we want to take a look at that. Yep. So let's say we want to take a look at the background task and take a look at the properties. We can see the average value here, same as what's being reported in the statistics. And we can also view where in the timeline did the max and the min value occur, and we can jump to that location to try to see what else was active at that point, to try to pinpoint. So the min value for the background task would be the max value for the CPU load. Okay, we can export this data as well. Okay, now let's take a look at the XML file, and we'll see the expressions that we're recording here. Okay, so you can see that we're importing the ORT file, and then we are defining some tasks here. The Core 0 task, the ISR 2 load, Core 1 task load, and then we have an expression, which is the variable that we're going to be sampling. And the other option here, the other important setting, is the sample pool. So this is the number of samples we'll take before we make an average. And so you can change that. It's basically like the period setting in the hardware trace menu for the CPU load inspector. I'll show you. All right, let's take a look at the hardware trace now and see what kind of information we can get there. Okay, so we've just opened up our AGBT active probe workspace. Let's go ahead and connect to the target. Okay, so we're connected here. Let's go ahead and run the system. Just make sure that things are running. Okay, everything looks good. Okay, so now let's go to the analyzer. We're going to go View, Analyzer, and let's configure the analyzer here. Okay, so we have the profiler set up. We have it set to trigger immediately. We're using the on-chip timestamp source. Let's take a look at the hardware configuration. So we've got the Aurora trace port set up. We're using just one lane at 2.5 gigabits per second. We're still connected through DAP at 100 megahertz. Okay, so this all looks fine. Okay, let's also take a look at the profiler configuration. So we are set up to record code, and we're also using an OS objects file. It's iSystem XML. Okay, let's also take a look at the OS file that we have set up. So we have an iSystem XML file using a profiler instrumentation. So now that everything's set up, we can go ahead and start a new session. And it's set up for just a 500 millisecond recording. And so we've recorded that and we've uploaded the data here. Okay, now that we've recorded our session here, we can take a look at the results. So let's go ahead and expand out. We've got all cores, threads. Let's zoom out in time. And let's take a look at the CPU load results. So we've got our average, min, and max. Let's actually move this here. Okay. So basically what we've recorded here is all the threads of all cores and all the runnables of all cores, and then we've calculated the CPU load. And so we've only recorded 500 milliseconds, 516 milliseconds. And we can see that most of the load is on CPU 0. There's some load on CPU 1, but CPU 2, 3, 4, and 5 don't have very much load. We can also see that reflected here in the average, max, and min. So we can see, yeah, CPU 0 and CPU 1 carry the most load. And so now let's take a look at the actual configuration. So here under post-process we have inspectors and CPU load. So right now it's set up for a 1 millisecond period. And so we can see if we expand this. So one millisecond is probably the lowest I would recommend, unless you have a system that runs very fast periodic tasks or other functions or routines that are very, very quick, then you can use a lower period. But let's expand it up to maybe 100 and see what kind of results we get. Okay, so the average is always going to be the same because the average is calculated over the entire measured time. So just the min and the max will change based on the period that you've set up. We can see that the max values have actually lowered. They're actually similar to the average value. Since we only recorded 500 milliseconds, we're basically just dividing that 500 into 5 different samples, and we're averaging over those 5 samples. So if you use a larger period, then the min, max, and average will be much closer to the average over the whole measured time. So let's go on the other extreme, which is to lower the period past, let's maybe try 100 microseconds. Yep, okay, so we can see the average is still the same, but the min values have all gone to 0, which means that we've basically taken samples of just the idle time, and so it's going to come up as 0% executed. And then we've also taken samples of just execution time, so those will be the min and the max times that are going to be reported. So the time slice, or the period, is too low to get any useful min and max values, but what is useful is the graphic that you see. And so you can expand out threads and runnables if you wanted to. It is a lot of data. But then you can try to look at specific areas of high CPU load and maybe zoom in, like maybe under here. And then you can see what runnables were active at that point in time, what threads and which CPUs. We can organize things in a certain way. Okay, so this provides CPU load, then thread data. So it just allows you to try to pinpoint exactly what's going on in areas of high load, and to try to focus your attention to possible problematic areas. Okay, so let's zoom all back out. Okay. But it just provides a nice, more visual view of what the system's doing over time. So that's sort of the nice thing about the being able to profile the data on the timeline. And then of course the statistics you have access to as well. So, but the statistics is where you really have to kind of fine-tune the period to get, and it also depends on what you're actually looking at. If you're looking at a finer level of what's happening, then you're going to want a smaller period, a shorter period. If you're going to want to look over the system as a whole, then a longer period would probably suffice better there. Okay, so that's the new features for CPU load sampling, as well as the new CPU load inspector for hardware trace. Thank you. First of all, I hope you enjoyed this webinar and found it beneficial. In summary, we went over a simplified definition of CPU load for embedded systems. We found out how to measure CPU load using 4 different methods: user instrumentation, operating system instrumentation. Both of those add some overhead to the system, whereas using a hardware trace with the new CPU load inspector and the new sample-based profiler don't require any instrumentation and can get accurate results very quickly. And you get a profile of the whole system for better timing analysis when you need to investigate a local overload.
All right. Thank you, Chris, for your demonstration, for sharing all your knowledge with us. Thanks for also sending some questions. And before we really start with the Q&A session, you have now the chance to download the presentation by clicking the cloud symbol top right of the screen. Chris, the features you presented are part of WinIDEA. WinIDEA is part of our base units IC 5000 and 5700. Are these features working with both base units or only with one of them?
Yeah, so these new sample-based features are only available on the 5700 platform. Both passive and active probes are supported. But the 5000 does not support the new sampling based features, but you can do hardware trace still with the 5000. It doesn't support the active probe, so it doesn't have that FNet connector that's required for the active probes. But you can still do a passive probe and get hardware trace with the 5000 and do CPU load inspector measurement that way.
Okay, but if customers have an IC 5700 and a trace activation key, they can immediately start.
Right. Yeah. Then you don't even need the trace port. You can do the sample-based profiling and get some data right away without any effort at all.
Yeah. Right. And is this feature a generic one? So you used for both examples a TC399 board. Questions came up. Is it working with TC2? Is it working with Renesas? Could you explain a little bit more in that direction, please?
Sure. Yeah. So as long as we can sample data while the system's running, then it should work. So the bottleneck there is the debug clock. So for the Infineon case, their chips actually support a higher clock on the DAP port than some devices do. So some devices will work better than others just because of the DAP clock speed. But yeah, pretty much any device that you can sample data while the system's running, you could use this feature to measure CPU load.
I could only imagine that maybe some old S12 or RL78 or something like that could be a little bit problematic.
Right. Yeah. So in those cases, the debug port might be an older technology, and I'm not sure if you can actually monitor things when the system's running. Like you need at least somewhat of a modern device where they have like dual ported RAM, so you can be reading the system while it's running. So a modern device is preferred. You could still do some kind of instrumentation method for like an older device. So there's ways to get CPU load. You'd have to use one of the other methods possibly.
Yeah. And is it also generic regarding the OS, or do I at least need to use an OS? So I know it's AUTOSAR OS focused, but is it generic vector, ETAS, for example, Electrobit, or also as a second part of my question, is it possible without an AUTOSAR OS in theory?
Yeah, no, definitely. Yeah, so CPU load is not something unique to an operating system, although it makes it much easier to calculate because you already have the idle task. So obviously the easiest way to calculate CPU load is using the idle task. And so an operating system will have that idle task or background task. And so that's the easiest way to get the CPU load. But even if you're not running an operating system, if you're just running some kind of bare metal scheduler or something, there should be at least the lowest priority task. And so you can use that as the idle task, and you can calculate CPU load from that. So yeah, you don't need an operating system to do the calculation. It would just require a little bit more instrumentation on your side if you don't have that idle task already.
Yeah. Cool. So generic in all ways. Chris, which version were you using? I think some 9.20, so not a 9.12 as our attendee states. I think this is, as you said, it's a new feature, so I can imagine it's not available in the older builds.
Right. Yeah. So this is only available in our newest 9.21 versions. I think you need at least 9.21.22. In the demonstration, I was using 9.21.32 actually, but I think 9.21.29 is the latest available from our website at the moment.
Okay, so it's always good to use one of the latest builds, and then you also have the new features available. You can also watch out our webinar about 9.21 WinIDEA version. So it's a big change. The handling changed quite a lot, and Chris did that some months ago, when it's also hosted on our YouTube channel. And if you want to upgrade or just check it and evaluate it, so reach out to your iSystem representative or contact person. So let's come back to the Renesas MCU, or not directly to the Renesas, to the generic MCU. The second question came in about the generic feature regarding the controller architecture. So what I understand is that we could use it for any MCU with a good sampling rate on the debug pin. The only thing that we should manage would be the interface with the debugger you have presented.
Right, exactly. So yeah, depending on, for example, on Renesas, so Renesas sort of has a special interface called the LPD. It's like a low pin debug mode, and so that's their own proprietary debug port. And but you can stream data over that port. And so Renesas actually has a special instrumentation that you can do with any of their chips. So they've created a similar solution for trace. It's called a software trace that you can instrument very easily. They've got some special instrumentation instructions for that. We have some white papers that go over that. So yeah, you could take advantage of that. So as far as I know, any modern device you'd be able to do this with. It really doesn't matter who the manufacturer is.
Yeah, so we can also continue discussing this offline with the exact CPU you're using, and then we can really figure out what is possible with your CPU and how it is possible with a CPU.
Right.
All right, Chris, I have a question still. You mentioned the iSystem XML file. You used it as an alternative to the ORT file. Where do engineers get this XML file from?
So the XML file has to be created. So that's not something you can just download from somewhere. We have a specification that you can use, and we also provide this as a service too. So if you need help writing the XML file, or just need some information about the format that we use there, we can get you that information. So yeah, it's something that has to be created for you.
Cool. All right, I'm running out of questions. Our attendees are running out of questions. I think everyone is happy, and then I'll come to an end, or we'll come to an end. Chris, thanks again for being our speaker, for sharing your knowledge, for being here in the Q&A session.
Yep, my pleasure.
Thank you, everyone. Thanks again, Chris. If questions come up, feel free to reach out to your sales or tech representative at iSystem. If you don't know who this is, send us an email to webinar@isystem.com. Then, was a pleasure. Thanks, everyone. See you next time. Bye and take care.
Thank you. Bye.